Greetings, my name is Daniel Smith, and I'm going to take you through an introduction to TrenchBoot and follow it up with a review of our roadmap. So, what was the motivation for TrenchBoot? So to set the stage a little bit, in 2014, I was tasked to deal with a gap in the OpenXT upgrade. Specifically, a physically present attacker could tamper with and persist during the upgrade process. And what I was asked to do is come up with an automated forward sealing solution that would close this gap. And what that meant was when the update was occurring, I added a calculator that would pre-calculate the PCR values of the upgraded solution. And then I would seal the encryption keys for the system to the projected PCR values. And so that way, when this upgrade was complete and the system began to reboot, then the system could just continue the boot as normal, go through the measured launch, unseal the keys, and continue operation without any intervention by the end user. So when I was building that solution, I ran into several frustrations. And just to give a quick recap of those, the first was that the DRTM implementation that was available at the time was limited in what it could measure. It was fragile in how it handled those measurements, and there was a degree of complication to integrating it into your project. And then the few solutions that were actually using the DRTM at that time were more or less unique solutions that were specialized to their use case. And so that just made reuse difficult to do, if not impossible. And in this case, it forced me to have to write an entire solution from scratch. And then on top of it, the DRTM capability itself was being underused and underappreciated. There was research out there showing the potential of what could be done with measured launch and DRTM in particular, and nobody was really looking at these things. And finally, between Intel and AMD, both of which had DRTM capabilities built into their chips, the AMD chips, there were no existing tools out there outside of some academic implementations that allowed you to use their DRTM solution. And so with all of this going on, all these frustrations I ran into, and having some discussions with colleagues and everything else, in 2017 I decided we need a universal measured launch is what will help. And when I proposed this idea, I proposed it as in the idea of being a framework that would allow implementers to be focused on using the measurements as opposed to how to gather and the process of dealing with the changing of measurements and all these factors, right? So, and then we wanted to make it so that a way it was ubiquitous whether you were doing an SRTM launch, a DRTM launch, or even both. And so that was the original concept that I had, and I set with that, and after a year of working through that, I proposed the TrenchBoot project. And I proposed it at the Platform Security Conference in 2018. And in that presentation, the first thing I did is I walked through what a measured launch was and how you used it with a DRTM, or how a DRTM was used to do a measured launch. And then I discussed a few points, which is, at the end of the day, SRTM was already standardized. It was already being integrated into the major open source system boot related projects. And so what I was proposing is that we bring DRTM up to that same level of standardization and adoption. And then on top of that, we could then build an approach that would be a framework that allowed people to build SRTM and DRTM security solutions. And so what does that really make TrenchBoot? TrenchBoot is just a meta project, which is focused on building a cohesive capability across multiple external projects. The product of TrenchBoot is not a releasable product. The product of TrenchBoot comes in the form of patch sets that we submit upstream to other open source projects. And we're doing those patch sets, we're building these capabilities within these existing projects to provide a unified and interoperable approach to measured launch, both SRTM and DRTM. So when you've heard any of our past presentations and we talk about TrenchBoot enabling framework for building security engines to perform launch integrity, this is what we're talking about. We're talking about making our system loaders and our system kernels work in a similar manner for measured launch, so that a set of libraries could be made for system implementers to use to build measured launch solutions that meet the needs of their use case. It will increase reuse and it'll unify how this is done. In doing that, we're also building a unified approach to doing a DRTM launch across all the major open source projects. And the reason why that's important is that SRTM launch it's static by its nature. It's pretty fixed on how it's done, right? Whereas a DRTM launch, it's by its nature is dynamic and can be done at any time during system runtime. And so there's lots of ways it could be started. And so what we're trying to do here is unify that so that way you can take any system loader and use it to do a DRTM launch of any kernel on any DRTM enabled CPU. Now, when that's all done, the success of this project is not measured by the number of releases we make or how often we make releases. It's measured by how many projects we're able to get this capability upstreamed into. And then as an ancillary goal of the project is that whenever possible, we want to influence the hardware and software ecosystems to unify around a common way of doing launch integrity. And so with all of that, with understanding where it came from and what it is, we can go into and look at what we're trying to do, where we're moving towards. And that comes in the form of this roadmap. When we sat down to build this roadmap, what we did was we took a look across both the hardware and software landscapes. And when we're looking at these, we basically said, okay, what is it that we're currently doing? What is it that we want to do next? And what are the just general things we want to see happen, whether it's done by us or somebody else? And so we collected all this together into a spreadsheet and we called it our roadmap, and we've published it here in our documentation repository. And so like I said, we built this spreadsheet up, and the spreadsheet has multiple tasks laid in there. And when we identified some of these tasks were things that we didn't know if ever would be possible. But there's still things we'd like to see happen. And these were our halo tasks, which we colored in a light blue, as you can see in the legend here. And then there's these things that we want to do, but there's a lot of roadblocks, a lot of hurdles that are going to have to be overcome to accomplish them. And these are the things that we refer to as having hard to fill dependencies. And these we shaded in yellow. And the remaining tasks, more or less, we viewed as things that were just a level of effort and would just take time to get done based on resource availability. And finally, when we were laying out the columns in the silos that you'll see in a moment, we put a time based or a time factor to these, and it's a time factor in the sense that tasks that we put higher in a column means that these are things we want to see done sooner, and the things that we put down lower in the column is tasks that we foresee will be further down the road before they're able to be worked. And so, with that understanding of how this roadmap came about and how things are laid out, let's start to take a look at it. So, the first area we want to look at is the hardware space. And the hardware space is really more of an area where we would like to seek influence more than we would seek to make contributions. And obviously, the reason being is that the hardware space is owned by the silicon manufacturers and the OEMs and the device manufacturers, and so making contributions to them are less likely. There's less areas to do that, whereas providing input and asking for changes is more of what we would see in this area. And so, with that understanding, we can move over here to the first two columns, which is the ecosystem and the supply chain. So, the ecosystem and supply chain, the tasks in here, these are tasks that we already have elsewhere. We copy these over into these because these are not just tasks that we want to do, these are tasks that we are seeking for assistance from the ecosystem and for the ecosystem, the actors in the ecosystem to help promote and move forward. So I'm not really going to cover the first three in these here. We'll touch on them later. The one that is here is a research paper that is being discussed amongst a few of the contributors to discuss some of the areas around the AMD architecture and some things we'd like to see and some things we'd like to help with if possible. And so that brings us next to the silicon, where we're primarily focused on AMD and Intel. Right now, there's not a lot we have any big asks from Intel at this point. But from the AMD side, we have a couple of things that we would ask them to take a look at, and they're aware of already, which is the first is that for a secure loader on an AMD platform, it's initially protected by the DEF protection mechanism, and it's expected that the secure loader will then transition to an IOMMU DMA protection mechanism. Unfortunately, there's not a clean way to make that transition. And so there are some workarounds that we're looking at, and one of them will be what will be implemented initially, because at the end of the day, we need something from AMD and the silicon to assist in making a safe transition between these two protection mechanisms. The next one is the firmware TPM from the PSP firmware TPM. So we've ran into this on a couple of Ryzen platforms where the firmware TPM did not implement the locality for MMIO address spaces. And so for those that are not familiar, when you do a DRTM launch, the locality for is what's used by the CPU to signal to the TPM that it has entered the dynamic runtime, that the dynamic launch had occurred. And so that is a state at which the TPM clears the DRTM PCRs and allows it to take the dynamic core root of trust measurement to start up the process. And so without locality 4, you can't get into the higher localities and you can't do any of your DRTM measurements. And so the SKINet instruction will actually fail on these platforms. And so we'd like to work to get those fixed. So moving on to the commercial firmware area. So we've got this bend in two areas. First is the 3M their Desharo product line. An excellent open source based commercial supported firmware being produced by 3M that has a great security story behind it. As you can see here, you can see a lot of the things that they're working on And in their presentation, they'll go into a lot of this in detail and discuss this, and we'll do it justice in terms of explaining what they're accomplishing here. Which brings us to UEFI providers. So there's a few things that we would like to see happen in this space. The first being a proposal made by 3M Dev to Core Boot, but we would also like to work with the UEFI manufacturers and the UEFI community to standardize on a DRTM ACPI table. And the reason we need this DRTM ACPI table is because we'd like to standardize on the information that the preamble requires for setting up for a launch, as well as providing information to the post-launch environment on where it can locate certain items from the launch. So as I said, 3M Dev has made a proposal, done a proposal to the Core Boot community. We'd also like to work with UEFI and get this standardized and have UEFI adopt this table. The other one, which I think is already in progress, which is better or standardized on early configuration of the IOMMU for DMA protection by firmware. This really strengthens the SRTM story, and we would really like to see that in place. The next aspect is SMM containerization. As you can see, these two have a yellow shade into them, so they have hard to fill dependencies. The first one being for Intel, that's the adoption of an STM. So for Intel devices, we'd like to see an STM adopted. For AMD, this one's a bit interesting. So AMD has a capability called SMM Supervisor, and it is a SMM container solution targeted for hypervisors. It is by far the best freedom-preserving SMM containerization capability that I have seen for out there so far. It definitely gives the device owner a way to trust that they have SMM properly containered and cannot do a corrupt SMM cannot do any damage to their system. And so with that, that's our biggest ask for UEFI. So moving into the open source firmware, these are more areas that it's still things we need from the silicon providers, more so than things we're going to produce for the open source firmware community. So in these things, specifically to Intel and AMD both, open up your provisioning tools and provisioning process for the equivalencies of BootGuard on Intel and HVB on AMD. We need to get third-party open source firmwares able to use these technologies. They are a huge improvement to the security of SRTM, and we really would want to see open source firmwares being able to use these capabilities. When it comes to to Intel, one of the other things that we would like to see is the opening of the ACMs. Open source the code, and not only open source the code, but start working towards using a reproducible build for the ACMs. What that buys is the fact that if the code is open, the code can be audited, and if the build is reproducible, then a third party can reproduce and prove that that code is the code that is in the binary blob that we're being asked to trust as our core root of trust. So if you think keeping the code closed is giving you some security, it is not. Reverse engineers are really good. They will figure it out if they want to. Keeping the code closed buys you nothing. In terms of people abusing the code, nobody can create a properly signed ACM except for Intel. And so the fact that the possibilities of somebody creating a rogue ACM is highly unlikely unless somebody can break cryptography and fake signatures. And finally, one of the things 3M Dev is doing, as we highlighted for core boot, is they're working on this DRTM ACPI table that they're bringing upstream. So that is one of the contributions we're looking to bring. And so before we transition out of hardware space and into the software space, there is an intermediate area here, which is the hardware validation. The idea here is that we would like to produce a TrenchBoot validation test suite. What this would encompass is all the assumptions and expectations we codify in the solutions we send to the open source projects into a test suite, so that that test suite could be provided to silicon manufacturers and device manufacturers and OEMs, that they can run that test suite against the platform and know that if it passes the validation, then it can ship, and all the open source projects out there will be able to function on the hardware. So that is one of the where we want to accomplish in this domain. And so moving on to the software, the first area of software is the system loaders. So in terms of system loaders for UEFI, one of the things 3M Dev is looking to do is to add preamble support, DRTM preamble support, to the shims, to the two shim implementations that are out there, or one or both shim implementations. In doing so, when that is merged upstream, the next revision of the shim that's released and signed by Microsoft would result in being able to more or less directly DRTM launch your kernel from UEFI. Now with that, we move on to Grub. Now Grub was the original system loader we started with. It's the one we're still working on, and we will continue to support. Right now, Oracle is working in conjunction with Intel to build support for Intel preamble, and we'll be bringing that upstream soon. And you have 3M Dev, who has built the AMD support for Grub. When the Intel support gets merged, the AMD support will be refactored to align with what was done for Intel, and then merged into Grub, and so that way Grub will be able to do your DRTM launch for both Intel and AMD. Another system loader that 3M Dev has been supporting recently has been the iPXE system loader. They have an upstream or a AMD support patch set submitted to add the preamble to that. And so then again, we'd be able to DRTM launch from iPXE. And then the last area that we want to cover is the TrenchBoot's landing zone. This is one of the few actual things that's written inside of TrenchBoot. It's originated from TrenchBoot. The name landing zone was a temporary name we gave it, sometimes referred to as simply the LZ. That name was just given to it as a placeholder for the Git repository. Was not meant to be the permanent name, even though it's kind of started to turn into the permanent name. But that is being reassessed, and so that is why we're saying that there might be a new name here. So the LZ is an open source implementation of an AMD secure loader. And as we highlighted in the hardware section, it is inhibited by the issue of making the safe transition from dev to IOMMU. And so this is a task that we have out there where we're tracking the workaround fix that we're going to put in place, as well as when a fix shows up in hardware, we will then add that as well. One final task that's towards the bottom there that I want to highlight is being done by Apprentice eventually, and it was actually part of the original TrenchBoot proposal, is the concept of a measured secure boot. And what the measured secure boot is an attempt to address some of the fragile issues with secure boot. So that for those that are not familiar, Secure Boot starts with a key signature verification moving into a measurement solution if measurement is being used. What Major Secure Boot does is it reverses that approach, and particularly on BootGuard. BootGuard supports a measured only verification. So what you would be able to do with this, with a Major Secure Boot, is you would do a measurement of a component, who would then do your verification, and now that helps you deal with certificate key revocation and a lot of these other things that were exposed in Boothole, because now you're relying on starting with a measurement which you can validate off platform at any time, and it's free to change and can be easily changed, versus what you have with a verification process. And so with that kind of wraps up where we're going with system loaders, and now we're going to move into system kernels. So for system kernels, we'll start off with Zen. So Apertus has been contracted to help build a solution called HyperLaunch. HyperLaunch is going to change the way Zen is booted. There's a few reasons why we're doing this change. One of the benefits to TrenchBoot is that once this change goes in, it would enable the TrenchBoot style launch of starting an integrity kernel, which then initiates a security engine, which is what we've done with the Linux implementation. And then with HyperLaunch, we would be able to do that same kind of approach on Zen. And so once HyperLaunch lands, Apertus will then continue to work to add hashing and TPM support to the Zen hypervisor, so then we can then have that TrenchBoot style launch. For Linux, so Linux was the original targeted kernel for a TrenchBoot style launch. And particularly Oracle and Apertus have been working to upstream Intel support for DRTM into Linux. A patch set's been submitted. We've had some reviews. We have comments. We're working through those comments. And hopefully we'll have a revision of the patch set back out and deal with the next set of comments, or hopefully will be merged. Once the Intel support has been merged, Apertus will begin working with 3MDev to take their AMD patches, refactor them to align with the way the Intel approach works, and then work on getting those merged into the kernel. And to help those understand why we're taking this approach, so when it comes to the way DRTM works on Intel and AMD, Intel has a much more structured approach of what has to be done in the preamble, what's expected to be passed to the measured launch environment, and operations the measured launch environment is supposed to take, using Intel's verbiage for that. On AMD has a more open approach to it. So they leave a lot of that factor of that structuring that you need for doing the launch as an implementation for the solution provider. So what that means is that AMD gives us the flexibility that we can basically mimic the Intel's startup approach and structure in AMD, and therefore we would wind up with this same, like as we said in the core part here, this unified, cohesive way of starting the kernel from a DRTM across platforms, across architectures. So once we're done with Linux, the next area is KVM, Linux KVM. So for KVM, the big thing here to talk about is the introduction of SKINit and SEnter emulation into QEMU. So why would we want this? What this would do, or enable, would be you could do a physical DRTM into your KVM solution. Your KVM solution with this emulation in QEMU would then be able to provide a virtual DRTM to its guests. That means your guests can do DRTM attestations to network solutions that would like to see that. After that, one of the capabilities that we have in here that's underneath KVM, because that is the use case driving it, but is applicable to general Linux as well, is the kexec preamble support for DRTM relaunch. And what that is that means that your KVM system can initiate a DRTM launch into potentially an upgrade DRTM environment, for example. And that upgrade DRTM environment can then make the appropriate updates, any PCR adjustments, any sealing adjustments, and then itself could then do a DRTM launch back into the upgraded system. That provides you a strong upgrade story that can be attested to, and without incurring the overhead of a physical system reboot. And so that kind of wraps up what we're looking at in the near term for system kernels and the roadmap for system kernels. Which brings us now to Linux distributions. So Apertus and 3MDeb from the very beginning have been using Yocto as a means to build and test the secure launch capabilities for Linux. So in that endeavor, or in that vein, 3MDeb will continue to expand the layer, add platforms, expand the test cases that they have, and then we would work to get those layers merged up into the larger Yocto ecosystem. Then from there, looking at the other distributions here, we've focused on, these are the ones that we are focusing on at this point, which are Debian, Ubuntu, LFEdge, and Red Hat. Obviously, the big three are there because that will lead to largest adoption within the general Linux community. And LFEdge there is our representation for our IoT Linux distributions that we would like to help get adopt these TrenchBoot capabilities that we push into the upstream projects. So as we deliver these capabilities into the upstream projects, we would like these distros to be able to package them and make them available so that way the end user simply just needs to do a package install with a potential after install helper running to help configure the DRTM or launch integrity solution. So in that vein, we need to be able to work with these distros to get incorporated in their CI, get their packages, get packages built for them, get helpers built for them if needed, and get this all polished into their package repositories so it becomes available for end users. And so with that brings an end to the roadmap. And so where does that leave us next? And so what that leaves us is that while we've already had a lot of success and progress to date, there's still a lot of work to be done. And so therefore there's still a lot of ways for people to be able to contribute to the project. You don't need to just be able to write security code for integrity solutions. We need system administrators to help us build up system integration tools. We need documentation. We can also use configurations, and if you work with a distribution, we need help with it getting incorporated into the distributions. There's lots of ways that people can assist with the project. You can help, take beta builds of the solutions and help test them out. There's, again, lots of ways to help. And so in that vein, come join us. You can find us on the TrenchBoot channel on the open source firmware Slack. We have a mailing list. We have there's our website, and you can always just talk with us during the open discussion period during later today. And so with that, I would be glad to take any questions for whatever time we have left.